Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we are going to explore various qualifiers which can be used in C++ declarations. Qualifiers. As we started to develop this presentation, our idea was to talk about reference qualifiers. However, we quickly realized this was omitting some of the other qualifiers which exist. We decided to update the title of the talk from ref qualifiers to just qualifiers and provide a bit more diversity. So let's talk about the differences between a type qualifier, a CV qualifier, and a ref qualifier. We will also show an example which points out a surprising complication when using reference qualifiers.
The first category are the CV type qualifiers, where C stands for const and V indicates volatile. The purpose of these qualifiers is to specify whether a given variable, data member, function parameter, or some other entity is const or volatile. Since the volatile keyword is not recommended, we're not going to focus on it. The word mutable is a specifier and therefore not a type qualifier. When you mark a class member with mutable, it means that member can be changed even when accessing it from a const instance of the class. The inclusion of a single ampersand to mark the data type as L-value reference is not a type qualifier. The same applies to the two ampersands which mark the data type as an R-value reference. This is based on the definitions found in the standard. Looking at the first of our three lines of code, we are declaring a variable named var a, which has a const CV type qualifier. In our second example, we are showing a declaration of an L-value reference to an std string, which, as we mentioned, and based on the rules of C++, does not involve a type qualifier. The third line declares a const reference to an std string. Only the const keyword is part of the CV type qualifier. The next category is the CV qualifier. Notice the word type is not present here. This is because these qualifiers are not applied to a data type. They only work with non-static methods. When a CV qualifier is added to a given method, it restricts the implementation. Inside the body of a method which is declared with the const CV qualifier, class data members will be treated as if they had been declared as const. Another constraint is that no other non-const methods in this class can be called. The next point is a bit tricky to verbalize. A const CV qualifier on a method will not apply a const type qualifier on all of the data members. Any data member which was declared in the class with the mutable specifier will remain non-const, even inside the body of a const-qualified method. It is important to define and really know the differences between CV type qualifiers, which are part of the data type, and CV qualifiers, which affect non-static methods. The ref qualifier was added in C++ 11, and we typically call these reference qualifiers for clarity. Just as with CV qualifiers, these can only be applied to non-static class methods. If a reference qualifier appears on multiple methods with the same parameters, then overload resolution will be used to decipher which method ranks highest and will be called at runtime. To ref qualify a method, simply put one ampersand for L-value reference or two ampersands for R-value reference at the end of the method declaration. The reference qualifier must appear after any CV qualifiers. Since both the CV qualifier and the reference qualifier are considered during overload resolution, it is legal to have all three of the examples we are showing declared in the same class. The two L-value reference qualified methods are not ambiguous, since the last one is also const CV qualified. As a brief mention, The const makes the last overload a better match when the instance or object it is being called on is also const.
So the purpose of the reference qualifier is to add overloads. The best match will be chosen based on the value category of the instance the method is being called on. In the first line of our example, variable data A is declared as a QString and assigned some text. In the next line, the trimmed method is called, which makes a copy of data A and then removes all whitespace from both ends of the new string. The result is saved to data B. Since data A is a named variable, it has a value category of L value. This means the overload for trimmed with the L value reference qualifier will be chosen. This is a straightforward example showing how the process works. In this example, we are now calling the trim method on a temporary QString, which has a value category of R value. Since the object or string is an R value, the method declared with the R value reference qualifier will match and be selected during overload resolution. This property can be very useful since the implementation of these two trim methods might be completely different. The R value reference qualified implementation of the trim method does not copy the string, since the current object is a temporary and cannot be used after the current statement. Calling a method on an R value object can be very efficient since the existing data can be modified directly instead of allocating space for a copy. There are some startling issues that show up with reference qualifiers, and the details are really important. In this example, we have two classes, char A and char B. They have a parent-child relationship, as shown in the diagram. The relationship is required due to various design constraints for the definition of a Unicode character. The class QString can be thought of as a container of char B. In our first line of code, we are showing the declaration in class char A for the operator equals method. This is a standard operator overload, which implements an assignment. Notice this method is L value ref qualified. This is a good restriction, since assigning to a temporary would be useless, since the updated value would be thrown away almost immediately. The second line of code declares a QString with the variable name of result and initializes it with the value of pair. The third line of code calls the replace method, which changes the letter P to B. The string result will now contain the word bear, so everything is working as expected. It is the last line of code which has a problem. Our code compiles, and it should not. The bracket operator returns by value, which means result bracket 0 returns the letter B, which has an R value category. What our current line of code does is assign the character D to a temporary character B, which was not the intent. The purpose of this line was to modify the first character of the string, exactly like the call to the replace method. So why does this line of code compile if we are assigning to a temporary? We added the L value reference qualifier to the operator method, so this would be detected at compile time. We had no compiler errors, so we assumed our codebase was fine and we had no bugs. Then we found a string which was not being modified correctly. We were baffled and a bit confused. Our first thought was questioning how overload resolution worked. We knew this area of the standard was not broken, but maybe reference qualifiers are ranked differently. After a bit of research, we realized overloads were not the problem. It turns out the cause of our error is somewhat more surprising.
The assignment operator that was declared in class Char A is not just a method. It is called a special member function, and the normal rules of inheritance do not apply. There are 6 special member functions, and 2 of them are operators, one for copy assignment and the other for move assignment. If a special member function is missing, the compiler will generate it for you and call the base class version if that applies. Since we did not originally implement a copy assignment operator in class Char B, we assumed the parent class implementation would be sufficient. In our opinion, it should be. Unfortunately, when the compiler generates a special member function for you, the reference qualifier is not inherited or respected when the parent class implementation is called. If you have any class which supports either the copy or move assignment operators, make sure you declare these methods and L-value reference qualify them in both your base class and any inherited classes. If you are using a library and inheriting from a class to extend functionality, we strongly suggest verifying the source code for reference qualifiers. This odd behavior does seem like a flaw in the C++ standard. However, it cannot be solved easily, since some code bases might depend on the existing behavior. Thankfully, there is a simple workaround. You just need to know about this issue and remember to use it. For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, please feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.